Hello everyone and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
Firstly, I've got to say that I've got to make clear that I'm not a statistician. I don't have any formal qualifications, and therefore be cautious about taking on board everything you hear from me when I'm talking about statistics. This is simply based on my experience and my reading. Secondly, if you're a researcher or if you're a trainee planning to do research, you will often need to do some statistical testing yourself, and you can be assured that it's going to be very difficult for you to get expert statistical input, especially if you need input on doing simple inferential methods. And I think to a certain extent, everyone who's doing or anyone who's doing research ought to be familiar with some of the basic concepts of inferential testing. So the first thing to explain or reiterate is the difference between inferential and descriptive statistics. We talked about descriptive statistics before. Essentially, descriptive statistics provide a useful summary or summaries of the data in front of you. We've talked about this in our previous episodes, and if you are interested, it might be worth your while reviewing CRAMSURG chapters 13 to 15, where we talk about how we describe a data set. So, inferential methods essentially allow us to make inferences about the data. In other words, they enable you to test the hypothesis in front of you. The hypothesis will be based on the clinical or research question you have. We spent some time talking about hypothesis testing, p-values and confidence intervals, and again, it might be useful to go back and review those if you're not comfortable with these concepts. So hypothesis testing was in CRAMSURG chapter 1, p-values and confidence intervals were discussed in CRAMSURG chapter 17. When we talk about inferential methods or statistical methods that allow you to test hypotheses, there are some very straightforward, simple methods like the chi-square test and the Fisher's exact test and so on, and some complicated methods. And we thought it might be useful for trainees if we could discuss some of the simple inferential methods that people can then refer to and make use of these discussions whenever they are called upon to do these tests. So that's a brief introduction for what we're going to discuss today, which is the chi-square test. The chi-square test is also known by some other names, the Pearson's chi-square test, or the chi-square test of association, or the chi-square test of independence. So this is what we're going to talk about. There are some variants of chi-square test that I'm not going to elaborate on today, but I'll name those variants at the end of this talk. Essentially, this is a non-parametric test. So most statistical methods are divided into two categories, parametric tests and non-parametric tests. In non-parametric tests, you do not make any assumption of the way the data is distributed. Like, for example, the opposite of non-parametric tests would be parametric tests, which rely on the fact that the data is normally distributed. Here, for these non-parametric tests, you don't make any assumptions about how the data is distributed. And the chi-square test essentially looks for statistical significance of the association between two categorical variables. We talked about data types before, so I won't explain that in any great detail, but categorical variables are data that are grouped into categories. So it's not like measurement or continuous or quantitative data. So these are qualitative data types. It's always good to talk about these things with examples that hopefully surgical trainees and medical trainees can relate to. So I'm going to talk about thyroid cancer as an example. and essentially dwell on two aspects of thyroid cancer. One is the presentation. You could divide thyroid cancer patients' presentation into asymptomatic or symptomatic groups. We know that asymptomatic thyroid cancer is on the increase. We see patients where the cancer has been picked up on scans done for unrelated conditions or during investigation and treatment of benign disease such as Graves' disease or multinodal goiter. And we also obviously have the category of symptomatic patients. The patients come with a lump or with dysphagia or swallowing or breathing problems and so on. Now, when it comes to thyroid cancer histology, the vast majority of thyroid cancer are what we call differentiated thyroid cancer. That's the most common type and also the type with the best prognosis. And we think that a number of these incidentally directed cancer or asymptomatic cancer belong to this category. That's what we think. There are some other thyroid cancer subtypes, and I've listed them here. It's about 5 or 6 different types, but they're all really uncommon compared to differentiated thyroid cancer. So one of the questions people have had for some time and has been addressed in some studies is that is there a relationship between the mode of presentation, i.e. symptomatic or asymptomatic, and histology, i.e. differentiated thyroid cancer or other types? Another way of asking this question is whether the histological type vary by the mode of presentation. So that's the clinical question. So you've got 2 categorical variables here. One is presentation, asymptomatic or symptomatic. The other is histology, differentiated thyroid cancer or non-differentiated thyroid cancer. So let's suppose you have a data set and let's suppose you got the data on presentation and histology from around 270 patients, 271 to be precise. And you've got this table here, a 2x2 contingency table, wherein you show the relationship between histology as 2 separate columns versus mode of presentation as 2 separate rows. So this kind of table is a really useful way of presenting the relationship between 2 categorical variables. Now, what does this table tell you? Now, you could say that if you look at the overall total patients with thyroid cancer, regardless of the mode of presentation, 92% of patients have differentiated thyroid cancer. Yeah. In the asymptomatic group, that increases to 97%, and in the symptomatic group, it drops to 88%. So clearly there's a difference, and this table tells you that there's much more differentiated thyroid cancer in the asymptomatic group, which is kind of what most thyroid surgeons would expect. And the question then is, yes, fine, there's a difference, but could this difference in this particular study have arisen just due to chance? And that's why we need to test for statistical significance. So if your null hypothesis is that the histological type is not different in the 2 groups, which means your alternative hypothesis will be that histology is in some way linked to presentation, then you then have to decide on a specific statistical test that could look at the data and test the null hypothesis. Now, what test to use is a separate topic in itself, and that's based on the nature of the data, the type of the data, whether it's categorical or quantitative, whether it's normally distributed, things like that. The number of groups, here we've got symptomatic versus asymptomatic. In some instances, you could have 3 or 4 groups. So based on all of these different parameters, you then have to decide what statistical test to use. And I'm not going to go into the details of how you decide on what statistical test to use, except to say that in this particular setting, you use the chi-square test. Like I said before, this is a non-parametric test, and it's a test that looks at the association between 2 categorical variables. So let's look at the table again. So like I said before, you've got 92 or 91.5% of all patients have differentiated heart cancer. And the observed numbers in this particular study for the symptomatic and the asymptomatic are depicted in this table. Now, what you then have to think about is what would the expected numbers be, assuming that there's no difference in histology in the symptomatic and asymptomatic arms. And I've calculated the expected numbers based on the proportion of DTC and no DTC in the entire cohort of patients. So I've done the calculations for the expected numbers, what you would expect if you didn't see a difference. And then you have to be looking at the difference between the observed numbers and the expected numbers for each of these cells. So if you have a 2x2 table, you've got 4 cells. And for each of these cells, you look at what the observed numbers are in the study and what you would have expected if there's no difference in histology between the symptomatic and asymptomatic group. And then you calculate the O minus E, or the observed minus expected. You then have to look at, do some more calculations. Essentially, you take the square of the observed minus expected relative to the expected numbers. So O minus E square divided by E. And this gives you a magnitude of the difference between the observed and the expected. And you then add all of those. So you add the observed minus expected whole square divided by expected for each of the 4 cells. And then you get a number, which is essentially what the chi-square statistic is all about. So essentially what you've done so far in very plain simple terms, or as simple as I can make it, is you're seeing how much you would expect if there's no difference between the arms. And you're looking to see the difference between the observed and expected. And you're calculating the chi-square statistic. And the higher the chi-square statistic, the more the groups are going to be different. Okay, I hope that makes some sense. So essentially, that's what the chi-square statistic is. First, you obtain the square of the difference between the observed and expected values for each cell. Divide this by the expected value, and then add these values across all cells. And the value here is 7.32. Now, the next thing to do in understanding the principles of a chi-square test is to think about the concept called degrees of freedom. Now, I'm not going to go into the details of this concept. Suffice to say that the degrees of freedom gives you an idea of the number of independent pieces of information you have in a data set. For example, in a 2x2 table, if you have the total number of patients and you have the total row totals and the column totals, you just need one of these cells to be able to compute the other cells. Let's say you got 100 symptomatic and 100 asymptomatic people, and you get 50 symptomatic patients who have differentiated heart cancer. Then you can calculate the number of people without differentiated heart cancer, and you can even work out the number of people who are asymptomatic across the 2 histological groups. So this is what degrees of freedom are meant to do. If you're doing a chi-square test, then essentially the degree of freedom is number of rows minus 1 times the number of columns minus 1. Here in a 2x2 table, the degree of freedom is 1. And I apologize if this sounds a bit complicated, but you do have to know the degrees of freedom before you can calculate the probability or the p-value, which is what you want to get to at the end of this kind of analysis. So you have the chi-square statistic, you have the degree of freedom, and then you want to know what the probability is of getting the value of 7.32 or higher than 7.32 given the degree of freedom of 1. And in the days when we didn't have access to the software that we have now, you would look up a probability distribution table that kind of looks like this. I know this looks complicated, but essentially, on one hand, you have the degrees of freedom as the rows, and as the column headings, you've got the p-value, and you then have to plot your 7.32 against the degree of freedom, and you come here and you find that the probability that relates to 7.32 is between 0.01 and 0.005. So essentially you're saying the probability of getting a chi-square statistic of 7.32 or higher is between 0.01 and 0.005. In other words, the p-value is less than 0.01. Of course, you've got the software, a number of different commercial and freely available software that will do these calculations for you. But I thought I should explain the process so that you get a slightly better understanding of what actually happens when the chi-square statistic is being calculated. So another important thing for trainees and researchers to know is how to report on a chi-square statistic. Ideally, you have to give the actual statistic, the chi-square statistic, which is 7.32. You also have to mention the degrees of freedom. That depends on whether it's a 2x2 table or a different kind of table. You have to talk about the total number of patients or subjects or units of study, and then you give the p-value. Now, because the p-value is less than 0.05, which is the conventional threshold, you can say that you reject the null hypothesis. In other words, you can say that there is likely to be an association between these two variables, between the mode of presentation and histology. Keep in mind that the p-value only gives you an idea of the strength of statistical significance. It does not give you an idea of the strength of association. You know they are linked, and you're only expressing the certainty to which you know they are linked by giving a p-value or having a low p-value. But you don't know how strongly they are linked, if that makes sense. Now, there are a number of assumptions that that have to be met before you can do a chi-square test. And I'll just go through these assumptions fairly briefly. The first one is that the data in a 2x2 table should be frequencies. They shouldn't be percentages. You have to put the raw numbers in. The second assumption is that these groups are independent. So the groups in this example being people who are presenting with symptomatic or asymptomatic cancer. The third thing is that every subject or every patient contributes to only one cell, but the cells are mutually exclusive. So you should not do a chi-square test if you have some kind of variable that is being studied in a before-after situation. And finally, quite important, the numbers should be adequate. You can't have really low numbers in single digits and say you're going to do a chi-square test. Now, what numbers are adequate? Well, it depends on what reference you look up. But essentially, if the total number is less than 20, then a standard chi-square test is probably not ideal. If the numbers are between 20 and 40 and the smallest expected value is less than 5 in any cell, then again, you shouldn't be doing the standard chi-square test. If you have a table that's more than 2x2, i.e. table with a degree of freedom more than 1, then no more than 20% of the cells should be less than 5, and no cell should have less than 1, or no cell should be empty. So these are some rules of thumbs that you can use to make a judgment on whether you can do a simple chi-square test. And if the numbers are really small and not able to meet these assumptions, there are some other things that you can do, but that's outside the scope of this discussion. So a quick summary of some other tests that are very much related to the chi-square test. They're all listed in here. There's a chi-square with Yates correction and the Fisher's exact test. These are particularly useful when your numbers are really small. There's a chi-square test for trend. It's a test that you use when the groups are ordered. Like, for example, if you have cancer split across 3 grades, grade 1, grade 2, grade 3. Now, you know 2 is worse than 1 and 3 is worse than 2, so there's some ordering. So in that kind of setting, you could use the chi-square test for trend. There's a McNemar's test that is used for before-after comparisons. where you shouldn't use these traditional chi-square tests. And then there are two other slightly related but slightly different sort of chi-square tests which relate to different settings. One is the chi-square goodness of fit, and the other is the chi-square test of homogeneity. We'll talk about this in a later discussion. And if you are really interested, I would suggest that you look up these two short references that I put up on the screen. And they're quite easy to understand and easy to follow. Okay, that's it. Any questions? Any feedback is useful. The last thing I want to do is go on about concepts that people don't find useful or interesting, and people don't value them. There's not much point doing these kinds of things. These are quite dry subjects, so I guess unless you practice them, you're going to forget them. But hopefully it's a useful reference to look up as and when you need it.
I certainly would think so.
Okay.
Should we do a quick demonstration?
Yeah. Oh, yeah, I completely forgot that. Yeah, let's do the demonstration. Right. So let's have a look. So Gio is going to put up a freely available software called Jamovi. And you can tell us about that, Gio, and show how you would do a chi-square test on the same example.
So yeah, we'll make it super quick. So Jamovi is a completely open source and freely available software. You can find it on jamovi.org. You can probably see my browser window on the shared desktop as I speak. You can also use it in the cloud, so you can just play with it, just put some random numbers in it and have a go and see how it works, or you can just install it. I use it fairly regularly for a lot of my projects. And very quickly, I am going to use the same data set that Prof used to create this this analysis. Okay, if you, like most people, keep things on an Excel sheet, you can very quickly just import it by using the special import function and then clicking on it. And as you can see, even a fairly sizable data set like the one that Prof sent me and used for his example gets imported fairly quickly. Now, because I made some changes to this data set after importing it, and I've already saved them, I'm going to open the one that I've got here. Right. So to do a chi-square is actually fairly simple. It comes as a bundled test. There's loads, and we'll discover the functions of Jamovi as we go along in the next few sessions. But you just go on frequencies, independent samples, chi-square test of association, and you can spot pretty much straight away that the other tests here that we mentioned, like chi-square goodness of fit and the McNemar's test. You find the variables that you're looking at. So we looked at symptomatic or not, and we put it in a row. And then we go down and look at DTC or not, and put it in a column, and simply look at the results. So as you can see, this table matches the one that Prof. Saba had on his presentation earlier on. As you can see, very simply, it gives you a chi-square value as well as p-value. And you can also do more things, plots and other statistics that you can potentially add on as you need them. I think given that it's freely available, and given that you can just download it and have a go at it, I will probably just experiment with it and see how you find it. It is a very useful software. It's based on R, which I'm sure a lot of you will have heard of. Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.